So, hello everybody again, and welcome to video lectures on operations research. And we are now in chapter 8, dealing with so-called duality. And before going to duality, we consider different forms of LPs. So in the last video lecture, we transformed this kind of non-standard LP 8.3 into a standard form LP 8.4. Here there was a typo here, so this was their min, it should be max. It's now corrected. And let's just recall here, what do we mean by standard form LP? We mean the form 8.1. So we have a problem that's a maximization problem, and all the constraints related to this technology matrix A and upper bounds B, yes, the B's are really upper bounds. So we have a sign like this here, upper bound less than equal to, and we have sign constraints for all the decision variables x's, so all the x's are positive or or non-negative, to be more precise. All right, let us then, before going on, I make a small exercise here, 8.5. So standard and non-standard LPs with GLPK. So the GLPK does not need a standard form LP. It can be a non-standard form also. And just to check this, so I ask you to solve both the non-standard form LP 8.3 of the previous example, this one here. So model this with Octave and solve it with GLPK, or try to solve. Something funny will happen actually. And then do the same with this LP 8.4. So model this with matrices for Octave and solve it with GLPK. So you should get the same solution, and you will, I guess, you will get the same kind of something went wrong message from GLPK. And then there is another point here. So what happened? What went wrong? So to understand, ask the full outputs from GLPK. So optimal decision, optimal value, the error number, and the extra parameter with all its fields. And if this does not help, you want to tune a little bit the workings of the GLPK. So maybe the MSG level, that's the message level, you might want to turn this to maximum so that the GLPK tells pretty much everything what it's doing. And the reason why something went wrong could be that the GLPK tries to do some dirty tricks in the pre-solver, so maybe you also might want to turn this pre-solver off to really see what's going on here. So what is the hiccup with GLPK with this kind of LP? Okay, so the example 8.2 here, so where we transformed LP 8.3 into standard form LP 8.4, that was relatively simple, so no real algorithm or careful analysis was needed. So let us then have something that's, I should say, pretty nasty LP. Pretty nasty in the way that it's pretty far from a standard form, and maybe we need an algorithm or a bit more careful analysis how to transform this into a standard form. Okay, now this is 8.6. It's titled as a problem, just so that we have a different section for its solution. You might think that the problems, as you notice, these are kind of big examples here. So we consider the following LP 8.7, and here are Roman numerals to refer the lines. So it's a minimization, so something that is not standard. It has a lower bound here, something that is not standard. Then it has double bounds here, something that is non-standard. Then it has equality here, certainly non-standard. And finally, sign constraints are only for x1 and x3. So x2, there is no sign constraint there. And to emphasize that, there is this line x2 URS. Okay. About that, I want to emphasize this. So 8.8 remark URS. So what do I mean URS? So of course, if you look at this, this is actually a redundant constraint. This is not a constraint at all. It's just there to emphasize that this x2 is URS, meaning unrestricted in sign. Okay, it's clear from this sign constraints 5 because there x2 is missing, so only x1 and x3 are restricted to be positive, x2 is not. Alright, so why do I have this redundant or constraint saying that there is no constraint? The reason is that the sign constraints are so typical, and even in standard form we assume them, so it's maybe sometimes a good idea to emphasize something that is not there. So this is there just to emphasize that x2 does not have a constraint. Alright. So how to write this in a standard form, this 8.7. And we will have an algorithm 8.10, it's given below. And following step by step this algorithm, this will be transformed into a standard form. And everything else in this algorithm, I mean steps 1 to 3, it has 4 steps, are probably quite obvious, but then there is this final step, step 4, where we deal with this unrestricted in sign variables. So how do we impose sign constraints to x2? And this is a kind of trick that's probably, I don't know, new to many of you, so I will consider this trick, which is actually a general trick, a bit before showing you the algorithm. And this is the remark 8.9 here. It's called positive and negative part. And this is a kind of, I believe, I hope that this is obvious and even trivial once you see it. The funny thing is that something this trivial is very useful in many places. So if x is any real number, I mean just some number, I can always split it into its positive part and negative part in the following way. I can always write x to be x plus minus x minus, where the thing is that both these x plus and x minus are positive, or actually non-negative. Actually what will happen is that one of them is 0 and the other one is not. And how do I do this? Well, it's simply that x plus is a maximum of x and 0, so this will be x if x is positive and 0 otherwise. Okay, and x minus is the negative part, so if it's a maximum of minus x and 0, which is just a way of saying that x minus is minus x if x is negative. That is, well, it's the absolute value of x is negative, and if x happens to be positive, then this is 0. Okay, this is, I mean, it looks very complicated, the notation, but it's a very, very simple thing what happens here. So for example, 42 is 42 minus 0. Okay, 42 positive part is 42 and negative part is 0. So minus 7, what is this? Well, this is 0 minus 7, yes? So the positive part is 0 and the negative part is not the minus 7 but the 7. Okay, so this minus here is the same as here. this minus here. Alright, that was a trick of splitting anything, any number, into its positive and negative part, so that the positive part is positive and negative part is positive, and the minus sign in between takes care of the negative sign. And this is useful in many cases. So in LP it's useful, you will see, in the algorithm of turning something like this into a standard form in step 4. And let's see what is the algorithm. So think about this LP, and indeed this we will turn this into a standard form soon. And in order to turn this into standard form, we have to make sure that it's a maximization, all the bounds are upper bounds, and finally we have sign constraints everywhere. So how do we do this? Here is an algorithm called LP standard form algorithm. And again, it has some fancy looking formulas and subscripts and so on. Let's see if we can make it slightly bigger, so it's easier to read on the screen. Let us make it so big that it fits the screen but does not go over. Okay, here it is. So 8.10 algorithm, so-called what I call LP standard form algorithm. So the idea is that we take any LP, follow this algorithm, and having done that, we should have a standard form algorithm. And actually it's not completely necessary that you follow these steps in this order. You can do it in a slightly different order also, or it's not necessary to follow this algorithm at all. Of course, you can maybe be clever and do something else, but this is at least an algorithm that should work. So if you are unsure how to do it, use this algorithm. So step 1, change into maximization. So if the objective is to maximize, already, do nothing. This step is done. If the objective is to minimize, change it to maximize by multiplying the objective by -1. So this is actually what we did in the previous example. So min z equals C transpose x turns into, so this is what I mean, this wiggly arrow, maximization, so maximize minus z equals to minus C transpose times x. So that's a relatively easy, straightforward and quick step to do. Then step 2, remove double inequalities. So we haven't had this before, but sometimes it so happens, maybe the modeling is like that, that in some constraint there are double inequalities. So we could have something like this. So I here is the ith row in the block, or the ith constraint. I can go from 1 to whatever, how many constraints there are. So we have to, for each constraint, so start constraints from the top and go to bottom and check if there is a double constraint. So meaning that Li, L like a lower bound, less than equal, then there is a technology matrix coefficients times the decision variables x1 plus blah 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 up to a ith row and column of the technology matrix xn, and this is less than equal to ui. So how do we deal with the double constraints? Well, actually, if you think about even the word double constraint, it means that there are two constraints. This here is nothing but a compact or short way of saying that we actually have two constraints. We have that lower bound, this is less than equal to this stuff, and this stuff is less than equal to this stuff. So what I have here is the same as what I have here. So we turn this into this. So if we have a double constraint, we will write this as two constraints, because that's what it is. Okay. And then a kind of funny way of looking at it, but this is just for us, for our formalism this works. If we have an equality, so left hand side equal to right hand side, something like this here, formally this is a double constraint, a double inequality, sorry. So this left hand side equals right hand side is the same that the left hand side here is the middle here. It is both bigger than equal to this bi and less than equal to bi. I mean, we can formally do this. And the idea is that we want to have the standard form for one reason or another. So we just do this. If you want to solve this LP by hand, or if you want to solve this LP by GLPK, there is no need to call this standard form anyway. Usually it's not a good idea. And if you want to calculate by hand, which is to begin with not a good idea, but if you for some reason are forced to calculate or solve the LP by hand, then of course changing this kind of equality into a double equality is probably the most stupid thing you could do, because equalities are very nice. I mean, this kind of equality you immediately actually can solve or reduce one variable there just by solving it in terms of that. So these are actually, from the practical solution point of view, these are nice constraints. But we are now not trying to practically solve this LP. We are trying to rewrite it in a standard form. And why do we care about standard forms? I mean, theoretically or general consideration, it's good to have one fixed form of LP, so it's easy to understand everything in a fixed form than to have different standards and different forms. Okay, that's it. So equality is a double equality like this, and then it actually, if I have something equal to something, it will turn out into two constraints. The something is greater than equal to something, and also at the same time less than equal to the something. Alright, suppose now that step 1 and step 2 are done. So we at this point we have a maximization LP, and we only have single inequalities at every line. But the single inequalities, they can be lower bound or upper bounds. And we only want to have upper bounds. So how do we remove the lower bounds? Or we don't remove them. Maybe this is not a good way of saying it. We transform them. Of course, the bound is still there, but it looks different. So, if there is a lower bound constraint, say Li, in some row I, then we change it to an upper bound by, yes, you probably have guessed it. We multiply the inequality by -1, obviously. So, if we have something like this, Li less than equal to whatever it is, we turn it to minus whatever it is less than equal to minus the Li. Okay. Yeah. And now the last step. So if we have followed step 1, 2, 3, what we have now, what we should have is an LP, that's a maximization, and all its constraints are upper bounds, meaning that you have technology matrix times the decision variables is less than equal to some fixed number. And now we have to impose the sign constraints, and this is maybe a bit, how should I put it, tedious step to do, or at least something where you easily make a mistake. So how do we impose sign constraints? Well, we use the trick that there was a remark. We split the decision variables into the positive and negative part. And this has to be done for each URS, unrestricted in sign variables. So let's say if variable xi is not restricted in sign, we replace it everywhere with xi plus minus xi minus. And then these xi plus and xi minus are restricted in sign to be positive. So we actually we increase the number of variables formally. Of course, in the solution, because this is how we split it, in the solution one of those will be 0, at least one of those. Okay, so this is the algorithm, and let's now see how it works. Let's make this text a bit smaller. I hope you can still see it. I hope you have good enough eyes. I wanted to make it smaller because there are, okay, this will take some space in the notes, so let's hope you can see most at the same time. All right, so we have a non-standard LP like this. I have repeated it here. So here is the 8.11 solution that is non-standard LP. So here I have done nothing. I have just copy pasted it. I mean, it's for convenience to have it here also, especially if you're not printing out these notes, then this costs nothing. And if you do, then okay, it'll cost a little bit paper, but let's face it, paper grows on trees or is recycled. Hopefully the latter. Okay, so here is the LP we are starting with. Let's start with step 1. Okay, it is a minimization, so we have to multiply the objective, which is here the Roman numeral 1. We multiply it by -1 and change min into max. So this is what is done here. So the first line is only thing it has changed, and I put there whenever I do something that changes the way it looks but does not change the way it effectively means, I put a prime there. Little, yeah, what does it call? Hyphen, I suppose. No, not hyphen. Quote. So 1 and 1 prime are actually the same thing, written in a different form. And this was step 1, so I didn't do anything else at this step. So this was just, rest is copy pasted. And the point to understand here is that this LP is the same, although it looks different than this LP, meaning that its solution is the same. Alright, so now we can forget the original one and we look at what we had after step 1. So we can consider this. Then we have step 2. We have to remove double inequalities. So where do we have double inequalities here? So at this point we are going through all these constraints and see if this step 2 applies. Well, the first one is, well, it's not fine if we think about it in terms of a standard LP, but let's not consider it yet because it's not a double inequality. Here we have a double inequality. 2 less than equal to x1 plus 6x3 is less than equal to 40. So this we have to split into 2 inequalities. And this is the 3, so it's split here 3.1 prime and 3.2 prime. Let's go further. In the constraint number 4, well, it's not third constraint, but line 4 on this LP, it's an equality. So this we have to understand that this is a double inequality, so it means that this thing here is both greater than equal to 50 and less than equal to 50, and then this means that it becomes 2 inequalities. This here is less than equal to 50 and it's also greater than equal to 50. or 50 is less than equal to this. So this is what is written here. So 4.1 prime, 4.2 prime is the same constraint as 4, but now written in the form that they are only single inequalities. Okay, what happens next? Next is something that's in the algorithm it was not so clearly stated, but it's kind of obvious if you think that we want to represent everything so that there are on this side are only x's, or all the x's are on this side, and this side there are only numbers or constants if you like. So it means that we just flip this over so that this 2 comes here, and remember that the sign will be then the other way around since we flip it over. And same for this 50. Okay, so now this stuff here, step 2, we have written it in this way. So all the inequality signs are all here, nothing here. Here are some numbers, and here are some x's with numbers. And the step 2 is now finished. Okay, what about the step 3? Again, now we can forget the previous LPs since this is the same as what we started with, and we have to remove lower bounds. So we should not have inequalities of this way. And do we have them? Well, let's start. We have already here in the first constraint, that is the line 2, we have lower bound 21. Okay, we turn it into upper bound here at 2 prime simply by calculating everything by -1. So 9 becomes -9, 5 becomes -5, -3 becomes +3, less than equal than 21 becomes -21. Let's then go to the 3.1 prime, that's okay. Then 3.2 prime prime, that's not okay, has to be multiplied by -1. This is precisely what happened here, so that this is now 3.2 prime prime prime. That's okay. Now 4.1 prime, it's an upper bound, that's okay, nothing to be done there. 4.2 prime prime, it's a lower bound. Okay, we have to multiply by -1. This is what happened here. So now this is 4.2 prime prime prime. The sign constraints are there as they are, and the unrestricted inside is there as it is. So nothing has been done to them yet. Okay, we are nearing the finish of this transformation. So step 3, removing the lower bounds. It's here. Note that this we don't remove. That's the sign constraint. That's how it should be. And now it's the step 4, which I said that it's kind of the nasty step, especially in the way that it's very easy to make mistakes here. At least very easy for me. Let's hope it's not so easy for you. Alright, what happens here? Now we are looking at the sign constraints. So x1 and x3 are okay, but x2 is not okay because it is unrestricted in sign. So we get rid of this, you can call it anti-constraint if you like, line 6. So how do we get rid of it? So we replace x2 by x2 plus minus x2 minus everywhere. Everywhere where it we see it, we replace by this with this subtraction or sum. And then with this we add the sign constraints that they are positive. And to make completely clear what happens here, I do this in two steps. So in the first step, I just did what was asked here. So this is really a search and replace. I actually formally did this with my editor as a search and replace. So whenever there is x2, I replace it by x2 plus minus x2 minus. So this is what happened. So if you look at these blocks here and these blocks here, so that's precisely what happened there. And then now x2 is no longer there, so this anti-constraint will be removed. But for x2 positive part and x2 negative part, they are both positive or non-negative. Actually, I will replace that here. So now we have a sign constraints 5 to 5 prime. Okay, formally this is, yeah. So 5 and 6 are the same as 5 prime now. And I have this here. And then what is the last step or sub-step to do? So the last part of step 4 is, again, now this is not written in the way that we want to write LPs, in the sense that we don't have nicely the variables in columns and inequalities in rows, so in a nice tabular form. So how do we do that? We just open these parentheses here. So 10 times x2 plus minus x2 minus is of course the same as 10 times x2 plus minus 10 times x2 minus. And this is what happened here. So maybe I'll scroll it a little bit back so we can see the final step. And then I put there just small primes to show that we have changed or rewritten the lines in a different way. And now, is there anything to be done? No, we are ready. So we have to maximize. Okay, there is the minus sign there, minus z, to make the comparison to the original one. So if we solve this, then the solution to the original one is not this but minus this. Here is the objective function. Then we have the constraints. All of them are upper bounds as they should. And we have sign constraints to all of the variables. Maybe a final point here, since we had this unrestricted in sign for x2, if we had it also for x1, for example, then we have to do this for x1 also. So this would make maybe the LP wider, and if we had it on x3 also, we have to do this for that also. So we have lots and lots of more dummy or auxiliary variables, so it's again wider and wider. So they are, at least formally, if you look at them, rather nasty things to do. And also, for example, in this case where we only have this unrestricted in sign for x2, then when you look at the solution, now we have 4 decision variables, and of course in the original problem we had only 3. So we have to interpret the solution a little bit, and how to do this. So we get then the xopt, say it's a vector of dimension 4. So the x1 will be what it is. The last one is actually x4, it's the 4th one, that will be what it is. And then the second and third one. So the x2 is now split into the second and third decision variables, and there we have to pick up the correct decision. And how it will be, so if the x2 turns out to be positive, so then here in x2 plus there is a positive number. Okay? And that will be the x2. So if the x2 turns out to be negative, then we will have a 0 here for x2, and x2 minus will be some number, and this is the negative part, so the solution for x is the minus that. Okay. Or to put it more simply, in the solution, the second and third variable will be together. They tell us what is the x2 and what's the x2. Well, I mean, obviously it's here. X2 will be the second minus third decision variables in the, say, GLPK solution. All right. So that was a relatively lengthy problem and its solution, how to turn something into standard form. I hope it's now clear how to do it, and also I hope that you are it's somehow clear that there is some point in doing this, although we don't necessarily need it for solving LPs, but to understand what's going on and to compare with LPs, it's kind of good thing to have them all in the same form, and this is the one form I call a standard form. Of course, I could have chosen different forms also, and indeed in the following video lectures we will look at the different standard forms. Okay, see you there. See you in following video lectures. Bye.